Welcome back to AERO 1020, Theory of Flight. This is a short presentation on the drag equation and how to calculate drag. In order to calculate drag, we first need to know the coefficient of total drag, which equals the coefficient of parasite drag plus the coefficient of induced drag. So induced and parasite drag both combine to make total drag. There are coefficients of induced, parasite, and total drag, just like there's a coefficient of lift. Unfortunately, the coefficient of parasite drag can't be calculated very easily because it's usually found in wind tunnel testing. So that coefficient, the coefficient of parasite drag, will always be provided for you. However, we can actually calculate the coefficient of induced drag. But before we can do that, we first should review how to calculate aspect ratio. Remember, on a rectangular wing, aspect ratio is the wingspan divided by the wing chord length. So for a wing that has a 40-foot wingspan and a 3-foot chord length, the aspect ratio would be 40 divided by 3, or 13.333. If you don't have a rectangular wing, you could still calculate aspect ratio using a different calculation, that is the wingspan squared divided by the area of the wing. In this case, that would be 40 squared divided by 120, or 1600 divided by 120, and you get the same result, 13.333. So knowing the aspect ratio, we can now calculate the coefficient of induced drag. The coefficient of induced drag equals the coefficient of lift squared over pi times the wingspan efficiency, which is usually given as a percentage, times the aspect ratio. In this example, we are given the coefficient of lift as 0.8 and the wingspan efficiency as 0.85 or 85%. So now we can go ahead and calculate the coefficient of induced drag, and that comes out to 0.018. So now, given the coefficient of parasite drag at 0.27, we can calculate total drag, which equals 0.27 plus 0.018, or 0.288. So the coefficient of total drag in this case is 0.288. Now we can use the coefficient of total drag to calculate drag using the drag equation. And the drag equation is shown on the left of this slide. Drag equals the coefficient of total drag times 1/2 rho, which is density, times velocity squared times the surface area of the wing. It's interesting to point out that the drag equation is exactly the same as the lift equation, with the exception of the coefficient of total drag. Instead of the coefficient of lift, the drag equation includes the coefficient of total drag. Everything else is exactly the same. So if we were to use standard density of 0.00238 slugs per foot cubed and a velocity of 100 feet per second, we would calculate drag to be 411.264 pounds. And we would do that using the coefficient of total drag of 0.288 and the surface area of the wing of 120 square feet. So remember, the drag equation is exactly the same as the lift equation, except in the drag equation we use the coefficient of total drag rather than the coefficient of lift. So just like lift, drag is heavily influenced by velocity. Since the equation includes velocity squared, any increase in velocity is going to increase drag exponentially. Drag is also influenced by the area of the wing, influenced by density, as well as by angle of attack, because angle of attack will have an influence on the coefficient of total drag. That's the end of presentation number 16 on the drag equation. An important point to remember is the drag equation is exactly like the lift equation, except we use the coefficient of total drag instead of the coefficient of lift. And that everything that has an effect on lift in the lift equation has the same effect on drag.